Hello, everyone. Thank you for coming. My name is Dave. I am a freelance Android developer. I've been working with Android for about 8 years or so. And I am here today to talk to you about constraint layout. How many of you have heard of constraint layout? How many of you have tried to use it in the past? How many are using it in production? Okay, all right, good to know. Very good. That's about what I expected. So what we're going to do here today is really just kind of give you a good idea, hopefully, of an overview of what it can do. What is constraint layout supposed to do for you? What is it capable of? And we're going to talk a little bit about how it works as well to hopefully give you a good understanding of how things are going. So just to give you a bit of background for those of you who haven't been following along with it, Constraint Layout is an unbundled layout manager, meaning that it is not part of the core Android framework. It is distributed as a support library, which means that they can add to it, change it, and update it outside of the core lifecycle of regular framework releases. Okay? Currently, Constraint Layout is still in alpha. There was a release just this morning to Alpha 9. And it is my understanding that that will be the last API change release before they go 1.0, whenever that is. Okay? So for those of you who have not been using constraint layout in production, now may be a good time to start making and steering that ship a little bit and taking a look at that. Because the API, as far as I understand it, is getting close to being stable. They aren't expecting to make any more changes. They're only doing bug fixes at this point. So just something to keep in mind. So let's talk a little bit about what constraint layout is and why we need it. So pretty much all of us in this room are Android developers. We've probably built layouts something like this before, right? In Android development for UI, we have a ton of different layout managers that have a series of different rules associated with them: relative layout, linear layout, grid layout. Each one of these are designed to basically size and position views according to a series of predefined rules. And that works really well. It's simple to use. You can pick the layout that works best for your use case, and you can drop that in. What ends up happening, though, because these layout managers are a bit rigid, is that oftentimes you pick the layout manager that does the job best, and then you end up having to nest them inside of each other. So you may have a section of your layout where a vertical list makes the most sense. And you may have another section of your layout where it makes more sense to position those views relative to each other. And so the natural extension of that is to simply take those components and nest them inside each other. And logically, that makes sense. The problem with doing that is that from a performance perspective, nesting layouts is generally a bad idea. What nesting layouts effectively does during the layout and measure pass at runtime is it causes recursion as this framework drives down through your code to measure and lay out and position all of those individual views. So in general, the flatter you can make your view hierarchy, the better it's going to perform at runtime. This is significantly true on older devices or devices running older platform releases. Okay? So the primary goal of constraint layout is to try and flatten your view hierarchies as much as possible by giving you a layout manager that is extremely flexible and in theory should be able to do anything that you could have done with those other layouts, but doing it at one level deep instead of having to nest all these layouts all the way down. Okay, and I gave you a simple example, but in your applications, you probably have a series where these actually nest many layers underneath each other, especially when you're doing lists and things along of that fashion. So the goal of constraint layout is to turn all your layouts into this. Is that necessarily going to happen for everyone in this room? Probably not exactly, at least on the first pass. But what we're going to do is we're going to go through and see what constraint layout can do so that you can get an idea of how much of your view hierarchies can be flattened based on these rules. Okay? So the overall API surface area of constraint layout, I'm really going to break it up into two primary buckets. So we have a series of constraints that are associated with positioning views. And we'll look at those and we'll look at some examples. And then we have another set of views that are primarily responsible for helping you size your views. So we'll sort of look at those in a separate piece. And those two collected together really will give you a good idea of what you can do with constraint layout. And then to go a little bit deeper, we'll talk a little bit about the mechanics of the layout, just so that you can get some idea of how this stuff actually works when it's running on your device. Okay? So that's where we're headed. All right, so let's start with positioning constraint. So basically, I'm going to walk you through the majority of the constraint layout API surface area through a series of examples, just so that you can get an idea of what this stuff looks like. Now, I will make one quick caveat, which is those of you who have played with constraint layout are probably also quite familiar with the design view in Android Studio that goes along with it. It's a very nice pairing between the tool and the layout, and that editor does a very good job of helping you build these things. So I encourage you to try that out. But at least for our discussion here, I'm going to focus primarily on the layout itself. So I'm going to be showing you what constraints look like in XML, as opposed to all of these things potentially hiding behind the design editor that you may or may not have used before. So this is a really simple example of what a constraint layout might look like, just to give you an idea of some of the basic constraints. So the basic positioning constraints allow you to make connections between the various views in your layout and to the parent view itself. So constraints look something like this in their simplest form. It looks a lot like any other layout param that you might have used with relative layout or something like that. It's simply defining a relationship between one of the edges of this view, left, right, top, bottom, and I also support start and end, and a corresponding edge of a different view. Maybe it's a sibling view in the same layout, or maybe it's the parent. So you'll notice that you can reference a view by its ID if you want to create a constraint connecting it to another view. Or you can use the parent keyword to tell it that this is a constraint that connects this view to the parent constraint layout itself. Okay? Now, by default, when you define constraints like this, where a single edge of a particular dimension, whether it's horizontal or vertical, is constrained, the default behavior is that those two edges are going to align with each other. So if I create a constraint to basically align the left edge of my button with the parent, it's going to snap those two elements together with some margin, because they do support margin spacing, just like relative layout and some of the other layout managers. Okay? So in its simplest form, you can use these to simply align edges together. You can also constrain both axes or both sides of a particular dimension, whether it's horizontal or vertical. So if a view is fully constrained, meaning that both sides, whether it's the left or right or the top or bottom of a particular dimension, then the default behavior is that that view will be centered between those two constrained edges. Okay? And this allows you to not only just align elements, but also move them out and allow them to float freely within some constraint between these two edges. And as I said, the default behavior allows us to center a view between the top and the bottom, or the left and the right. So we can center views, or we can align them to other children. Great. We've just recreated relative layout. So if that's all we had, we didn't get much. Okay? But constraint layout doesn't stop there. There's a lot more in this API to help you out. The first is they introduce a concept called bias. Biasing a constraint allows a fully constrained dimension, again, meaning you have two connections on each side, to determine how that free space should be distributed on each side. So instead of just explicitly centering it in the middle, you can tell it that it should hang some percentage off to the left or the right or the top or the bottom. So that bias for either the vertical or the horizontal allows you to then shift that view between those two constrained edges. And I'm showing these examples in a fairly simplified fashion where this view is only connected to its parent. But if you have this view constrained to the edge of another view, that becomes the amount of space that is distributed between those two sides. Okay, so this is really between whatever the two edges are that this view is constrained against. This doesn't just work with centering it or laying it out in the parent, which is what you got with relative layout. Okay? So we have biasing constraints. We also have this little helpful feature called guidelines. This is another thing that you may have tried to trick relative layout into doing something like this before, but now it's a little bit more clean in the API. So a guideline technically is a view, but it's a very special kind of view. So when you put guidelines into a constraint layout, they define fixed reference points that you can use as the target for another constraint. So instead of just lining up my views with other views or with the parent coordinator or container itself, you can put these guidelines, either horizontal or vertical, anywhere you like. And these can be positioned using a fixed distance from the top or from the start edge, or as a percentage. So I can define these as, at 25%, 75% inside my layout, and those guidelines will then grow and shrink in their actual distances based on the size of the layout, the size of the screen. So guidelines allow you to apply these fixed reference points out there in the layout anywhere. So you don't just have to rely on the bounds of the parent or the other individual views. As I said, this is something you may have tried to do with relative layout by just inserting a view and giving it a size of 0 or something like that. Effectively, that's what a guideline is. It is a view that is always gone, so it's never laid out, and is always measured to 0, so it's never accounted for in measurements. Just gives you a fixed reference point that you can use as a target. And this becomes very helpful for lining up views. This is a very useful feature if you're trying to replicate a grid layout behavior, for example, where you might be building a form of some kind and you want to stagger those elements. You can use guidelines to create those constant reference points sort of in the middle there. Okay. So those are sort of the basic elements associated with positioning views. So we have the centering constraints, the biasing constraints, and the edge constraints, as well as the guidelines. Let's talk a little bit about how constraint layout sizes views. So again, we've all been doing Android development for a while. You're probably familiar with the 3 primary ways that you can size a view. I can tell a view, whether it's width or height, that it should be sized by wrapping its content. Effectively, that the size of the view should be no larger than is necessary to display the content inside of the view, whether it's text or an image or whatever it is. You can tell a view that it needs to be fixed size and give it an explicit dimension for its width or height. And you could tell the view to be match parent, essentially telling it that when it's measuring that dimension, it should attempt to measure itself at the same size of its parent container, or at least to fill the available space based on other layout rules. In terms of constraint layout, only 2 of these are supported. When you're defining your views inside of a constraint layout, you can use wrap content and you can use fixed size. But it's not recommended to use match parent. In fact, those of you who have played around with the tool, if you attempt to put match parent into your layout, the design view will take it and turn it into something else. And we'll talk about what that is in a minute. But they don't want you to do this. The reason is because if you use match parent, you might end up with something that looks like this. Now, what you have here is 2 examples. The top example up there is a view that is fully constrained on both dimensions, so on the left side and on the right side. And the bottom view is one that's only constrained on one edge. So the top view, when you use match parent, that's actually probably the behavior you were expecting. It should fill the available space minus margins between those 2 edges. But if you use match parent with a view that is not fully constrained, it matches the parent size in terms of that measurement, always. Which means if you shift it or do anything like that, it's just going to be measured off screen. Okay, it doesn't respect the constraints the way you might expect it to. So while you can technically sneak it in if you use the XML directly and you don't touch the design view, you're going to get weird behavior if you use match parent in general. So instead, when you're working with constraint layout, they've defined a new type to replace match parent called match constraint. Now, it's not really a new type per se. The idea here is that you would define that dimension, whether it's width or height, to just be 0. If you've used linear layout and worked with weights before, this is a common principle, right? The idea is, I don't necessarily care the exact size. I want you to fill the available space based on what's associated with the other constraints. Okay? So in most cases, when you said match parent, you probably meant this, which is why the design view goes through and makes that change for you. Okay? Match constraint, using the same example, instead looks like this. So with that fully constrained view, you get the same behavior. So if you were to do match parent or 0 DP on a fully constrained view, you would get that filling the space minus the margins. Match constraint, however, behaves a bit more like wrap content on a dimension that is only constrained on one edge, which is a bit more of a sane default than what we saw before. So generally speaking, wrap content, fixed dimension, and 0 DP, meaning match constraint, or you might also hear the term any size, are the three primary ways that you would apply sizes to a view inside of constraint layout. So the beauty of this match constraint is it allows you to create flexible size views, which is something that was, again, not necessarily easy to do with something like relative layout. You could do it with the weighted systems in grid layout and linear layout, but not necessarily in something as flexible as relative layout. So this allows you to define views that fill available space in a much more flexible way. Okay. Going back to some additional constraints, there are also constraint attributes associated with view size. Probably one of my favorite is the ratio constraint. Anyone in here who's written an aspect image view or something along those lines and had done that subclass before, it's gone, right? So now there's an attribute, constraint dimension ratio, that allows you to apply a fixed ratio to any view inside of constraint layout, okay? And you express it as a ratio, which in most cases actually makes sense, right? You'll probably use this a lot with image views, right? So you can define a particular view, and in order for this to work, the view has to have a fixed dimension or a fixed size in one dimension, so either wrap content or an actual size, and then be flexible in the other dimension, so effectively having 0 dp or match constraint. That allows the constraint layout to take that view and adjust that other dimension, the flexible one, to be exactly the appropriate ratio to opposite the side that you defined. Okay? Now this ratio is always defined as width over height. Okay, so even if you want one dimension or the other to be flexible, you would still define that ratio the same way. It is possible to define a view that is fully flexible in both dimensions, so both the width and height are 0 dp, and still use ratios. But when you do this, you should, sometimes you don't need to, but it's generally good practice to do this, you should modify the dimension ratio such that it has a prefix of either an H or a W in front of it. And what that will do is it tells constraint layout, since both dimensions of this view are flexible, which one of them should we consider to be locked to the ratio, and the other dimension will obey the particular constraints associated with that dimension. Okay? So you can do this if this makes more sense for your application, but in that case, you typically want to pick one of the dimensions that is ratio locked, and that's the one that you would put in a prefix there associated with the ratio. Okay? So no more aspect image view, it's gone. Constraint layout takes it away. I'll take questions at the end. Okay, another new feature. This feature was actually added in the drop that just released this morning, is layout chains. Okay, and this one is really cool because it allows us to reintroduce some other flexible concepts from linear layout and grid layout that the earlier iterations didn't have if you may have been playing with this in the past. So a layout chain is essentially just a group. It's a way of grouping child views and constraint layout together so that they behave as a group. Okay? Effectively, the way that you would define this is simply defining constraints in both directions between two particular views. So in this example, I basically just got 3 buttons that are laid out here. And the chain is created because the first and second button relate to each other using different constraints, and the second and third button constrain against each other. So we don't just have a constraint going one way, we have a second constraint going back the other way. When that happens, a chain or group relationship is applied between those two views. And there are 2 things that constraint layout allows you to do when elements are grouped like this. The first is you can apply weight. So this is something you couldn't do until we had chains. But now, using constraint layout, we can group the elements together that we want to fill the available space the same way you would have done with linear layout and weight. And you can apply the new weight attribute to have it fill the space in whatever proportion makes sense for your application. The other thing you can do, which I don't have an example of here, is you can pack the group, which basically just tells constraint layout that any constraints that are applied on the outside of this group should apply to the group as a whole. So now you could take a row of buttons and you could center the row, as opposed to having to try and individually define the constraints so that it makes the 3 buttons look like they're centered in a row. Okay? So grouping is very powerful in allowing you to apply outside constraints to a group as a whole And in order to do that, you connect them together using chains, which again is just a fancy way of saying the two views constrain to each other in the same dimension or on the same edge. Okay. All right, I briefly want to talk about the constraint set API. This API has a fairly specific use case. It's primarily helpful in animations. So you can think of constraint set as a helper for layout params. So just like with any other layout, you could typically go through and programmatically define the layout params associated with a particular view rather than doing it in XML. You could do the same thing with constraint layout. In fact, you could do it directly with the individual layout params because as you may have noticed, all of those attributes that were in XML are prefixed with that layout underscore, which means they're going to end up in layout params. So I could do this all in Java code without any XML. But constraint set allows you to take that a step further and allows you to group those constraints for a particular layout into an element that you can apply as a batch. And again, this has a fairly specific use case that helps you with doing scene transition type animations. So just quickly walk through the API. Constraint set is something you would create in Java. And then you can fill that set either manually by applying the individual constraints and their edges the same way you would in XML. You can pass it a layout file, which will read in all of the constraints from that layout and fill the set that way. Or from Java code, you can just pass it a reference to a constraint layout, and it will fill all the information from there. It basically takes a snapshot of all the constraints that are currently in that layout associated with all the particular views. Then you can take that and you can define sets for each particular scene in whatever transitions you want to apply. And then using the scene transition framework, you can just apply a given set to the constraint layout. And when you do that inside of a delayed transition, it will animate the change of all the constraints. So this is a very helpful utility for doing scene transitions with constraint layout if that fits your particular use case. Okay. All right. So that's sort of an overview of the basics of the API, right? So we have the sizing constraints, the positioning constraints, all of these things effectively defined in XML. When you're using the layout editor, or the graphical design editor, effectively all that tool is doing is filling out your XML file in a similar fashion that you would have done with relative layout or anything else. So doing this even directly in XML is not terribly scary. To be honest, I spend more time working with constraint layout directly in XML than using the design editor. That's just a choice of mine. So let's talk a little bit about how this stuff is all put together. How does it actually work? So just like any other layout, a layout is typically responsible for a series of views. So the layout has a relationship to all of those views, and each one of those views has attached to it a series of layout params. And this is true for any layout, whether it's linear layout, relative layout. The params inside of there will change, but the object itself is always attached to every child view. No different with constraint layout. As I mentioned before, all of those attributes from XML are going to be stuffed into the layout params for the particular view. So if you were to go look at these elements in the debugger or something like that, you would see all of those fields from the layout attributes that you would define on your constraint layout inside of your XML. Now, what they've added to this is that inside of the layout params, there's also this new object called a constraint widget. And this is the object that at runtime is responsible for resolving those constraints from a bunch of rules that you've defined into the actual size and position information associated with the view when it needs to be laid out. Okay? So the constraint widget is an element that is initially empty, but it's just attached to every single layout params instance. Okay, and we'll talk a little bit more about what happens after that. There's also this new element attached to the constraint layout directly called a constraint widget container. And we'll talk a little bit more about that in a moment, but essentially it's the driver for this whole system. So just like child views are attached to their parent layout, these child widgets are attached to the constraint widget container, and the container is responsible for driving the whole analysis process. Okay, we'll look at that in a little bit more detail in a minute. So what's inside of one of these constraint widgets? Well, what happens is during the layout process, all of the attributes that were in your layout params get stuffed into this constraint widget. And they get translated into a number of different things, but most of them are set up as these constraint anchors. So everything you set in XML gets turned into one of these attributes on the constraint widget. And then there's a series of empty attributes for the view's size and position information. So when the layout pass initially begins, all that stuff is stuffed from layout params into the widget, and then the remaining fields are empty. Okay? Hold that in your mind. Then effectively what happens during the measure stage and the layout stage of constraint layout is all of those constraint widgets are collected together. And the attributes associated with them are fed into a magic box. And we'll talk about what this thing is here in just a little bit. But there's this equation solver thing that reads in all those constraints, analyzes the rules that you provided, and out the other side pops sizes and positions. And those get stuffed back into those same widgets. So that widget becomes both the input and the output storage for this particular layout engine. Okay? So once measure is complete, all of the size and position information is done and has been computed for all of your views. So that means every time the constraint layout has to remeasure for any reason, it goes through that whole process again. Then during the layout pass, those constraint widgets are retrieved again, and this time that X, Y, width, and height information is just going to be applied to the individual views. So it turns out layout is actually quite cheap, because here all the heavy work, which again really isn't even that heavy, but all that work is being done during measure. Okay, so during measure is where we see all the constraints analyzed, and then during layout, it's just taking that information out of these individual widgets and just applying them to the views. Okay. So let's take a little bit of a deeper look at this magic box. So what you may or may not be familiar with is the fact that constraint layout actually gets its name from mathematics. So constraint layout is so named because all of those individual rules that you define are turned into rows or constraints in a system of linear equations. Okay? There's a whole bunch of math that goes on inside of this thing. So each one of those rules that you define, whether they're to position a view or give it a size, et cetera, they turn into constraints or rows in a giant system of linear equations. And then what constraint layout is responsible for is analyzing that system and solving those equations to give you the left, right, top, bottom values of every particular view. Okay? The algorithm that it uses is known as the Cassowary algorithm. It's a very well-known algorithm in computer science for solving linear equations. Those of you who have done any work on the iOS side, it is the exact same algorithm that is used with auto layout. It's also used in a number of other platforms. There are implementations in Python, Ruby, all over the place. If you're interested in learning more about it, there's a website, overconstrain.io, that gives you all types of places where the Cassowary algorithm is used, and you can kind of learn more about those implementations. Okay? So we won't talk too deeply about how that all works, but just to give you an idea, essentially everything that comes out of your rules. So there are constraints added for the size of the parent. So there are constraints that get turned into these equations for the parent itself. How should constraint layout be sized? There are horizontal constraints for each view, vertical constraints for each view, and then all of those sizing constraints. Each one of those just becomes another row in the table. And then once you have the giant table, the Cassowary solver can go through and resolve all of those values into something useful that you can use for layout. Okay? All right, so I'll give you just a real simple example because this can get really complicated really fast. But if we go back to the example that I had before of the single-centered button inside of a constraint layout, as it's walking through the process of filling that data in from the widgets into the solver, this is effectively the list of equations that comes out of that. So there's a block for the constraints of the parent itself. So what should be the left, right, top, and bottom value of the constraint layout? And these are fairly simple things, right? The left and top are the X and Y value, and the right and bottom are just those positions added to the width and height, right? But that begins the whole solving process. That information has to be part of the overall system. Then we add in the horizontal constraints. So we have one view that is fully constrained in that dimension. So it has these two constraints to both edges. And that's going to turn into 4 more equations, where again, the right value is fairly simple to figure out. It's just the left plus the width. But the other equations in there are a bit more flexible because this view is effectively centered and it may be biased to the left or the right. So we don't necessarily know right away that it's that simple of a calculation. So in this case, those left and right values are actually inequalities, where we know that the left has to be at least inset the margin and can't go far enough to go past the right margin, but in order to really make that determination, they have to add this final constraint, which you could also think of as the centering constraint, that if you do that math, pretty much guarantees that the left and right are always perfectly centered within the target, which in this case is the parent. If the target of those constraints was something other than the parent, then those values would be represented over here instead. And then if this were biased at all, you would see a factor multiplied in there to apply the bias left or right to those particular attributes. So you have all of those equations, and then a similar set for the top and bottom because we're centered in that direction as well. So the same 4 basic values, in this case, just now dealing with the top and bottom. So one view, 4 connections, creates 16 equations to be able to determine how to size and position that view. So you can see just by looking at this, the more views I add and the more connections I make, this list is going to get extremely long. Okay? So you don't necessarily want to do this analysis for anything too terribly complex, but it's interesting just to do in simple cases because you can get an idea of how this is actually working inside and sort of prove to yourself what it's trying to do. Okay? So I encourage you to do that. All right. One final thing that I just want to put a little bit of a bug in your ear. So I go back to this diagram that I had noted here before about how the hierarchy is put together. So we have this constraint layout and the views and et cetera, et cetera. But what if I reorganize it a little bit? So we know pretty full well that the relationship between layouts or view groups and the views underneath them, we have this sort of parent-child relationship that we could nest, and in some cases we do. It turns out, if you look at the architecture of the widgets and the widget containers, it has a very similar relationship, okay? Such that you almost wonder if you could do stuff you do with these, okay? Now, I don't work for Google, I don't know anything you don't know, but if I were to look in my crystal ball a little bit, I might say that it would be interesting, and I would say powerful, if you could define a system where you nest layout behaviors without actually nesting the layouts themselves. Sort of an idea of virtual view groups, right? So you have the behavior of a linear layout applied to a collection of views without having to actually go through the nested logic and the recursive logic of diving down into that layout. You could get the simplicity of nesting layouts without the performance hit. So I see this, and I see the way these things can be nested even though they aren't right now. And that tells me that this might be coming down the pipe. But I can't prove that. So I might be completely wrong, and you should probably ignore me. But what if I'm right? So keep your eye on that, and we'll see what happens in future releases. Okay. That's all that I have for you today. Just a couple additional pieces of information. There's my social stuff there if you want to connect with me. I have a sample project on GitHub, which you can find by just going to milehighandroid.com. It's the layout pancake sample. It's effectively just a series of examples on using constraint layout to provide what you would otherwise do with other layouts, like relative layout, grid layout, et cetera. So you can see it used, and some of these attributes and the examples I showed you were pulled from there. I also have a blog series that was done until they made this new release. I think I'm probably going to write something more on it on my blog. So wiresarobsolete.com. You can take a look at that as well. So let's see what do I have in terms of time. All right, I think if you have any questions, feel free to come up. I'm happy to entertain them. Otherwise, thank you for your time today, folks.